Hello friends, how are you? Hope you people are doing well. So we come up with next part and hope you have understood some concepts in last part. So we will proceed with some concept here and see how the number system is working in digital electronic. So let's start. The gray code The gray code is a sequence of binary number system which is also known as reflected binary codes. So it is called as reflected binary codes. Okay guys, the reason of calling the code as a reflected binary code is first n by 2 values compared to those of the last n by 2 values in order in values in a reverse order. In this code, two sequence values are differed by 1 bit of a binary digit. Means it is, if it is 0 1, next will be 1 1. Only one digit will change. Okay, it is like that. Okay guys, so if we'll start from 0 0, so 0 1, then 1 1, then 1 0 will come, because only one digit will change. Okay, in this, two consecutive values are differed by 1 bit of the binary digit. Gray codes are used in general sequence of hardware generated binary numbers. These numbers cause ambiguities or errors when the transition from one number to its successive is done. The code simply solve this problem by changing only one bit when the transition is between numbers is done. The gray code is very lightweighted code. So it is a lightweighted code. Okay. Because it does not depend on the values of the digit specified by the position. This is also called cyclic variable code. It is called cyclic variable code. Okay guys, why cyclic variable code? As the transition of the values to its successive value carries a change or of a 1 bit only. Okay, so if I want to change another, then it will come to 0 0, because only one digit can be changed. Okay, so this kind of cyclic things are done. That's why it is called cyclic variable code. Got it? So guys, we will see how to generate the gray code. The prefix and reflex method are recursive used to generate gray code of a number. For generating gray code, what we will do, we will find the numbers of bits required to represent a number. Then we find the code for 0, that is 0 0 0, which means as a binary. Now we take a previous code, that is 0 0, and change the most significant bit of it. Only most significant will be changed. So we perform this process recursively until all the codes are not uniquely identified. If changing the most significant bit, we find the same code obtained previously, then the second most significant will be changed. Okay, so let's see. So for n equal to 1, there is two possibilities, 0 or 1. So we will draw a line, we will write same 0 1, then we will this line will act as a mirror, so it will do 1 0. So next two digit code is 0 0 0 1 1 1 1 0. Okay, so it is like that. Or what he is saying, we will change 1 0 on this one, this least significant bit 0 to 1, and now we have to change only MSB, so it is 1 1, and then again least significant means 0 1, like this. So if we want to go for n equal to 3, what we will do, we will put these as the same as it is. We will put one line and it will act as a mirror, and we will copy it 1 0 1 1 0 1 0 1. Okay, so what we will do, we will write 4 zeros and then 1. Okay, so it is same 0 0 0 0 0 1 0 1 1 0 1 0. Now come 1 1 1 0 1 1 1 1 0 1 1 0 0. It is like this. We will generate, means it is a for 0, it is for 1, it is for 2, it is for 3, it is for 4, it is for 5, it is for 6, and it is for 7. So generally in binary 7 is 1 1 1, and in gray code, in gray is 1 0 0. Okay guys, so this kind of thing, it is important. So it is different from binary, so gray code. And gray code, where we use gray code will be used in K-map. Okay, sometimes they ask which code is used in K-map. It is gray code. Okay, we will see when we will see K-map also. Okay, hope you got it. Next is access 3 code. Okay, the access 3 code is also treated as access 3 code. So sometimes it is written access, it is written as sometimes access 3 code. The access 3 code is non-weighted. It is important, it is non-weighted code. It is non-weighted code. Sometimes ask only this non-weighted code. Okay, and it is a self-complementary, or it is a self-complementary. Okay, BCD code used to represent a decimal number. This code has a biased representation. This code plays an important role in arithmetic operation because it resolves deficiency encountered when we use the 248421 BCD code for adding two decimal digits whose sum is greater than 9. The access 3 code use a special type of algorithm which differs from the binary positional number system or a normal non-biased BCD. We can easily get access 3 code of a decimal number by simply adding 3 to each decimal digit, and then we write the 4-bit binary number for each digit of the decimal number. We can find the access 3 code of the given binary number by using the following step. And what are the steps? These are the steps. We will find the decimal number of the given binary number, then we add 3 in each digit to the decimal number. Now we find the binary code of each digit for the newly generated decimal number. We can also add 0 1 1 to each bit of the access. So what we will do, it is like that. If I want to calculate access 3 for 4, so I will add 3, so it is come 7. Now the access 3 of 4 is 7, right? So we will convert into binary. It is 1 1 1. Okay, we will put 1 0. So we will see 4 binary is this one, and or what we will do, 4 is 1 0 0 0 1 0 0, and we will add 0 1 1, means we will add plus 3 here, so it will be 7. So if we add this one, so we will get 0 1 0 plus 1 1 0 plus 1 1 0 plus 1 1 and 0 plus 0 0. so we will get 011 similar to that. So in this, either we will add 3 in decimal or we add 011 in binary, so we will get access 3 code. So for 0 we have 0011, for 001 we have 010, 0010 we have 0101, 0, so it is actually 3, it is 4, it is 5, 6, 7, 8, 9, 10, 11, 12. So for 9 it is 12, we added 3 here. Okay, so like this access 3 code will be generated. Hope you got it. Next, now we are taking example of a decimal number 31. Okay, so for 3 the BCD is 011, for 1 is 011. So for converting into access 3, in this 3 we add another 3, so it is now 6010. Okay, for 1 we add 3, so we get 4 like this. So similar type of thing is done. 1 is 0001, so we add 3 here and it is 011, 110 carry 1, 110 carry 1, 10, so it is similar to 4. Okay guys, hope you got it. What does it mean access 3? So we are just getting 3 extra. Okay, next we will see another example for 81.61. so for 8100, okay, so we will add 3 or 0011, so 1101, so it is 11. Okay guys, similarly it is 11. Similar 1 we add 3, we get 4, 6 we add 3, we get 9. Okay guys, so like this we added. Now we put same values here. So for 8 it is 1011, 0100, now point, then 616 is 1001 and 0100. So this is the access 3. This is the access 3 code of what? 81.61 decimal. So this conversion of decimal to access 3. So what we will do for this? First, decimal converted into BCD or binary. Okay, then it will convert into access 3 code. Okay guys, so it is simple. Hope you have understood. Okay, next is why we use access 3 code. So there are following advantages, and it is the property also. It is a self complementary. It is used code used biased representation, no limitation, arithmetic operation simples. The code 00001111 can cause a fault in the transmission line. The access 3 code doesn't use these codes and give an advantage for memory organization. These codes are generally unweighted binary decimal codes. The code has a vital role in arithmetic operations because it resolves deficiencies which are encountered when we use 8421 BCD code for adding two decimals those sum is greater than 9. Okay guys, these are the advantages. Okay, hope you have understood. So we will move now in number system. Signed and unsigned binary numbers. The integer variables are represented in a signed and unsigned manner. The positive and negative values are differentiated by using the sign flag. In signed numbers, the unsigned numbers do not use any flags for the sign. That is, only positive numbers can be stored in unsigned. Okay, so it is only for positive numbers, and it is for both positive and negative numbers. It is very easy to represent positive and negative numbers in our day-to-day life. We represent the positive numbers without adding any sign before them, and the negative numbers with minus sign before them. But the digital system, it has not possible to use negative sign before them because the data is in the form of binary. For representing the sign in a binary numbers, we require a special notation. So what we do in decimal, I want to write 10 plus 10 only, I will write 10. But for negative values of 10, I write minus 10. So we use plus and minus sign here. But that cannot be done in binary because everything is represented in form of 0 or 1. So sign must be represented in the form of binary 0 or 1. So we will do like that. So we will add a special bit. Okay, so binary number representation are this. Our computer can understand only 0-1 language. The binary numbers are represented in both ways, that is signed and unsigned. The positive numbers are represented in both ways, signed and unsigned, but the negative numbers can only be described in a signed way. The difference between unsigned and signed numbers is that unsigned numbers do not use any sign bit for positive and negative numbers identification, but signed numbers used. Okay, so for negative number special extra bit will be used. Okay, and what are the things for unsigned representation? Only 1 0. Here in signed representation, signed magnitude form ambiguous 2 zeros, 1 complement 2 zeros, unambiguous only 1 0. So we will see how it will be done. Okay, next, unsigned numbers represent the decimal number. As we already know, the unsigned numbers do not have a sign for representing negative numbers because it doesn't have sign. So the unsigned numbers are always positive. Okay, so unsigned numbers are only positive numbers. By default, the decimal number representation is positive. We always assume a positive sign in front of each decimal digit. There is no sign bit in unsigned binary number, so it can only represent its magnitude in 0 and 1. 0 is unsigned binary number. There is only 1 0 in this representation, which is always a positive because of one unique binary equivalent form of a number in unsigned number representation. It is also known as unambiguous representation technique. The range of a signed binary number is 0 to 2 to the power n minus 1. Okay, this is the range. Okay, so we will put 102 in unsigned binary number. So it is similar way how we are converting in binary. 102 is divided by 2, 51 remainder is 0. Likewise we will do 51, again 51 is divided by 2, we will get 25 and remainder is 1. 25 divided by 2 we get 12, remainder is 1. 12 is divided by 2 we get 6, remainder 0. 6 is divided by 2 we will get 3 and 0, and 3 will divided by 2 we get 1 and remainder is 1, and again 1 is divided by 2 we will get 0 and 1. So now we will write from down to up. So the number is 1100110. Okay, it is a binary form of decimal number 102. Okay guys, next, sign numbers. The sign numbers have a sign bit so that it can differentiate positive and negative integer numbers. The sign binary technique has both the sign bit and the magnitude of a number. For representing the negative decimal, the corresponding symbol in front of the binary will be added. The sign numbers are represented in three ways. The sign bit makes two possible representation of 0 for positive and 1 for negative. So if MSB is 0, then number is positive. Okay, and if it is 1, then number is negative. Okay guys, which is an ambiguous representation? The third representation is 2's complement representation, in which no double representation of 0 is possible, which makes it unambiguous representation. There are following types of representation in signed binary numbers. So it is, what are the signed magnitude form? 1's complement and 2's complement. In signed magnitude form, the binary number has a bit for a sign symbol. If the bit is set to 1, the numbers will be negative, else the number will be positive if it is set to 0. Apart from the sign bit, n minus 1 bits represent the magnitude of the number. So if it is a n bit, n minus 1, like this n bit representation. Okay, so these n minus 1 bits are magnitude, and this nth bit is sign, either positive or negative. So positive is 0, negative is 1. Okay guys, 1's complement, what we will do, we will invert each bit of a number. We can obtain 1's complement of a number. The negative numbers can be represented in the form of 1's complement. In this form, the binary number also has an extra bit of sign representing a sign magnitude. Simple forms still here. 1 is negative and 0 is positive. 2's complement form, by inverting each bit of a numbers and add plus 1. So it is actual, what is it is 1's complement plus 1. Okay, to its least significant bit. In LSB it is adding 1. We can add 2's complement of a number. The negative numbers can also be represented in the form of 2's complement. In this form, the binary number also has extra bit of sign represented as a sign magnitude form. So these are the things. Now we will see one by one all these. Okay guys, Now one's complement. In the binary representation technique, the binary number system is the most used representation technique in a digital electronics. The complement is used for representing the negative decimal number in the binary form. Different types of complements are possible of the binary number, but 1's and 2's complement are mostly used for binary numbers. We can find the 1's complement of the binary numbers are simply inverting in the given numbers. For example, 1's complement of a binary 1 0 1 1 0 0 1 is what we will invert it. So 1 will convert into 0, 1 1 0 0 1 0. So what we will do, we will invert 1 become 0, sorry. So this 1 becomes 0, this 0 will become 1, and similar to this 0 become 1, and this 1 become this 0, this 1 become this 0, this 0 become this 1, and this 1 become this 0. Like this we will do that. Okay guys, we can find the 2's complement of the binary number by changing each bit 0 to 1, 1 to 0, and adding 1 at the least significant bit. Okay, so we will see when we will see 2's complement. Okay, so here finding 1's complement of this one, so we will just change 0 to 1, 1 to 0. So see here 0 0 1 0 0 1 0 1 point 0 0 1 0. Okay guys, so this we will get. And here also what we will do, we will change 0 1 1 0 0 1 point 0 1 1 0. Okay, so like this we will do that. Next, use 1's complement in like this. So if it is plus 6 or minus 6. Okay, this is called LSB and this is called MSB. Okay, not this one, this is, or this is, okay, this is the MSB for that. Okay, so for plus 6, the number plus 6 represent the same way as the binary number. Okay, 1's complement plays an important role in representing the signed binary numbers. The main use of 1's complement is to represent a signed binary numbers. Apart from this, it is also used to perform various arithmetic operations such as addition and subtraction. In signed binary representation, we can represent both positive and negative numbers. For representing the positive numbers, there is nothing to do, but for representing negative numbers, we have to use 1's complement technique for representing the negative number. We have to represent it with a positive sign, and then if we find the 1's complement of it, let's take an example of this. Okay, plus 6 and minus 6. The number plus 6 is represented as a binary, is the same as the binary number. For representing both the numbers, we will take 5-bit register. Okay, so that plus 6 is represented with 5-bit register is 0 0 1 1 0. Okay, minus 6 is represented in the 5th bit register as follows. So it is now plus 6 we will take 1's complement out of it. So 1's complement is 1 1 0 0 1. Okay, so this 1 is represented as a negative number and it is only magnitude. Okay, so it is plus 6, it is MSB also and signed bit also. Now here it is MSB and it is a signed bit, that is difference in negative and positive number. Signed bit we have to add everywhere, and this is represented as a magnitude. Okay, so okay guys, hope you have understand. So similar ways, if I want to calculate for okay, well, let's take 120 and minus 120. Then for positive number, 120 is 0 1 1 1 1 0 0 0. Okay, so for minus 20 I will take the complement of it, so then it is 0 okay, so 1 0 0 0 0 1 1 1, so 3 ones only. Okay, and this 1 is represented as it is minus 20 120, so it is signed bit. Okay guys, like this we have to do that. Okay, so in simple way it is like that. Like if we say plus 3, so plus 3 is 1 1, so we'll add one more bit for positive sign 0 of, if we'll take 1's complement of it, then it is 1 0 0. Okay, like that. So one extra bit we need to be done. Okay, so next, 2's complement. Just like a 1's complement, 2's complement is also used to represent a signed binary numbers. For finding 2's complement of the binary number, we will first find the first complement of the binary number, then add 1 to the LSB, yani least significant bit of it. For example, if we want to calculate 2's complement of a number 1 0 1 1 0 0 1, so firstly we will find the 1's complement of the number, that is 0 1 0 0 1 1 0. Okay, now we will add 1 in it, so 0 1 1, this is 1 1 0 0 1 0, so it is a 2's complement of this number. Okay guys, similarly here, finding this number, change all 0 to 1 and 1's to 0, so the 1's complement of the number is, so 1's complement what is 0 0 1 0 1 1. Okay, now we will add 1 in this, so 1 1 0, carry 1 1 1 0, carry 1, then 1 again, sorry, 1 0 0. Okay, like that we have to do. Okay guys, so it is a 2's complement of that. Similarly here 1 0 1 0 0 1 1 0, So first 1's complement. So what is the 1's complement is 1 0 0 1 1 0. Now I will add 1. Add 1 is 1 1 0, carry 1 1 0 1 1 0. So it is a 2's complement of this. Okay guys, it is simple. Hope you get understand. So guys, this is the use of 2's complement. 2's complement is used for representing signed numbers and performing arithmetic operations such as subtraction, addition. The positive numbers is simply represented as a magnitude form, so there is nothing to do for representing positive numbers. But if we represent the negative numbers, then we have to choose either 1's complement or 2's complement technique. The 1's complement is an ambiguous technique and 2's complement is unambiguous technique. Let's see an example to understand how we will calculate the 2's complement signed binary numbers representation. So guys, we are taking again same example, plus 6 and minus 6. So we will take 5-bit register. So for 5-bit it is 0 0 1 1 0. Okay. For minus 6, first we will do 1's complement. What will do? We will do 1's complement. So 1 0 0 1 1. Now I will add 1. So it will become 0 1 0 1 1. Okay guys, so and the sign bit is 1, that means it is a negative number. Okay, so for positive representation same, it MSB and sign bit is same and it is the magnitude. And for negative representation, this is sign bit and it is a magnitude, and MSB is this one. Okay, so hope you got it. Okay guys, so we will stop this one is today here, and we will see some more things in next lecture. So keep watching. Thank you very much.